Okay, so let's dive a little bit deeper into what can be somewhat tricky notation when dealing with the sigma notation, specifically representing a Riemann sum. So this was the form we discussed in the last video. Notice I'm not necessarily looking at it including a limit right now because I want to try it in a more feasible example. So the first thing we're going to do is sketch the region bounded by the function f of x equals 2x and the x-axis from 1 to 2. So if we're graphing a slope of 2 essentially and going through 0, 0, so first just sketch the function. And then we're looking specifically along the interval from 1 to 2. So I'm not going to sketch my actual rectangles yet, but I'm saying we're focusing only on this particular segment of area. And they want us to look at this interval portioned into 4 equal parts. And so we're trying to decide, well, what would the width be of one of those intervals if we split it into 4 parts? And there's a formula you're going to do every time here, and it's hopefully pretty intuitive, but you're going to do the change from 2 to 1 divided by, in this case, 4, or whatever n subintervals you're asked for, to find out like how many things you need to slice it into. So in this case, it's just pretty straightforward. We're going to get 1/4. Okay, so I'm going to do my best here to make that happen. All right. And one thing I do want to point out is we always refer to the first number in their interval as A and the second number in their interval as B. It just so happens this example uses 1 and 2. So then part C says, if the interval from 1 to 2 is divided into n equal partitions, what would the width become? So again, you would look at your A and your B, you would find that change between them and divide it by however many subinterval or equal partitions they ask for. So in a more general sense, these widths we're creating down here for each rectangle would be equal to 1/n. If we call one of the subintervals the kth subinterval, right, and what they're saying here is like if I'm looking at specifically this subinterval, the kth rectangle out of all the ones we've, in theory, sketched in. If I'm looking at the kth subinterval, find an expression for the right-hand endpoint, so not the way I just drew it. If it's the right hand, let's see, that would go above a little bit. So if we're doing the right-hand endpoint, for the kth subinterval, we would start, again, it starts at A, in this case ours is 1, goes to B, which in our case is 2. They want us to write an expression using RA, which is 1. They want us to add R delta X, which in this case is 1/n, because we're saying in a more generic sense than this was just a specific example here to lead us to part C. We're going to keep it as general as possible, and we're going to say R delta X will just always be 1/n because our change from 1 to 2 is 1/n splits. Times K, we don't know what K is. That's the deal. It's some generic slice of the puzzle, whichever they may ask. And so that would be our equivalent of the expression they asked for here. And that would give us a very generic expression for x sub k, which, just to be consistent, I call it c sub k, some people call it x sub k, but we'll try to be consistent here. So that's their value for that. Substitute your expression above into the actual function, right? So the height of our rectangles is the output of a function that's given to us. So in this case, our function is 2x. So we're literally going to take this expression we just built, right, which again, I'm trying my best to illustrate this, sorry. It means we're starting with 1 and we're adding whatever this width is of our rectangles, k times, to get to the specific one that they are speaking of in a general sense. That was contradictory. Basically, we're trying to get it for any given slice. So we're keeping it generic with the 1 over nk. And we're going to plug that into the function. So in this case, our 2x, right, just remember that's our original function here, becomes f of 1 plus, and then 1 over n times k, I'm just going to call k over n, which we're going to say is 2 times that input. Just hang with me. I know this feels very random. It will make sense, I promise. So that's our generic expression for any slice. This is the function we're plugging it into because that will actually give us the height at that particular slice. It says now write the expression for the area of the kth rectangle, for the area. So let's recap real quick, right? We've got our base, 1 over n. We've got our position, and we've got our height based on the output of that position given the function 2x. So now we're going to put all of this together. Okay, so it's 2 times 1 plus k over n, and then the actual height is 1 over n. 1 over n. You know what, for color's sake, I'm going to put this in blue. Okay. Now at the end, we're going to put it all together. It says, finally, write the sigma notation for the area of the function using the limit definition. So I'm going to actually write mine above because I'm running out of space. So it would become the limit as n goes to infinity. And then we have our summation from k, we're using k. Sometimes you'll see i's or j's or other letters, but I tend to see k's the most. From k equals 1 to n of this beautiful thing we just built. So 2x was our function. So anytime you're doing these, you'll see the function, and then where you used to see x, you're going to see a parentheses with a bunch of stuff in it. I mean, like a bunch of gobbledygook, right? That gobbledygook always starts with, well, where did your interval begin? Ours began at 1. And then I'm going to add to that starting position my delta x, whatever that was. In this case, ours was 1 over n, k times. Like, I don't know how many of them I have, what exact position I'm looking at. But it's going to be, in this case, k over n, right? Or 1 over n times k. That's the height of the rectangle. And then times delta x, or times our change in x, which in this case is 1 over n, specifically because our interval goes from 1 to 2. But that top number will often change. It has to do with however, whatever interval you're looking at. So that's the limit definition, and then what we'll be doing today is kind of going back and forth between the two. So that would be equal to the integral, and then we're going to say the bounds from a to b, right? From a to b would be from 1 to 2 of our function, which is 2x dx. See how much nicer integration notation is versus summation? This is our nightmare. This is our dream. This makes us much happier. So the focus is seeing the connection between the two forms, right? We have our function. Our bound from 1 to 2 often shows up here as the first value you're starting at. That change between them is what has to show up here as well as here, since this also involved delta x just times a k. And then there's always something over n representing your delta x at the end, or the width of your rectangles. I'm sure this makes perfect sense to you now, and you'll have no problem in class.